Okay, so let's dive into the fascinating world of deep learning. We're going to frame this as a recipe, the ingredients, the blueprint, and the whole cooking process for creating something like an artificial mind.
So here's the fundamental question, right? How do you actually get a machine to understand something complex, like, say, what a cat looks like? Well, the secret isn't writing a million lines of code describing pointy ears and whiskers. No, instead, you just show it millions of pictures of cats, and you give it a way to figure out the patterns all by itself.
And this core idea, it's been around for a while. What you're looking at is the neocognitron from back in the 1980s. It's a key ancestor to today's massive AI models. And you can see the concept that really changed everything right here. A series of layers. Each one processes a little bit of information and then passes it on to the next. It's like an assembly line for perception, building up a more complex idea at every single step.
So, let's get to the first and most important ingredient in our recipe. Before we get lost in all the complexity, we've got to focus on the simple but incredibly powerful idea at the heart of all this, learning directly from data. It all starts with what's called a parametric model. The easiest way to think about this is that the code is your basic recipe structure and the parameters are the measurements. They're like the amount of salt, or flour, or sugar. They're all the little knobs you can turn that will completely change the final result.
So the whole goal of training the model is to find the absolute perfect setting for all those millions of knobs. And we do this by showing it tons of examples and measuring how wrong its answers are. That measurement of wrongness is called the loss. The entire training process is just this relentless, automated mission to get that loss score as close to zero as humanly, or well, mechanically possible.
Okay, so we have our core ingredient. Now let's get to the blueprint. What does a modern model actually look like? This is where the deep in deep learning really comes into play.
The blueprint is built out of these things called layers. Each layer is its own separate processing step, kind of like a station in a kitchen. The first layer takes the raw data, transforms it a bit. Maybe it just looks for simple edges and textures. And then it passes its work on to the next layer, which might combine those edges into corners or simple shapes, and so on.
And this is exactly why that depth is so critical. When you stack many of these layers, we're talking dozens, sometimes even hundreds. That's what allows the model to learn these incredibly complex and abstract patterns. A few layers might recognize what a whisker is, but it takes dozens of layers to learn the actual concept of a cat.
Okay, ingredients? Check. We have the parameters. Blueprint? Check. We have the deep layers. Now it's time to fire up the kitchen and actually start the cooking process. And for that, you need a seriously powerful engine.
The core algorithm that drives this engine is called gradient descent. The best way to picture it is to imagine that loss score as a giant, hilly landscape, and our goal is to find the lowest possible valley. Gradient descent is basically like taking a small step in the steepest downhill direction you can find, and then you do that again and again, millions and millions of times, until you've settled into the lowest point, the best possible settings for all your parameters.
And the scale of this whole process is, well, it's just mind-boggling. To train a single, state-of-the-art model for understanding images can take a quintillion, that's a 1 with 18 zeros after it, of these tiny mathematical operations. A quintillion. It's just a staggering number.
This is exactly why GPUs, graphical processing units, became the workhorses of the AI revolution. It's kind of funny, right? The very same chips that were designed to make video games look pretty turned out to be perfect for this, because they can do thousands of calculations all at the same time, in parallel. They are the perfect high-tech oven for our deep learning recipe.
So why? Why go through all this trouble? Why the massive models, the huge datasets, the planet-sized computational kitchens? Well, because the payoff, the results you get, have been nothing short of astonishing.
This led to the discovery of something called scaling laws. Researchers found this almost magical, predictable relationship. If you make the model bigger, you give it more data, and you throw more computers at the problem, its performance just gets better. It's not a shot in the dark. It became a reliable recipe for making smarter and smarter AI.
And the direct consequence of those scaling laws? An absolute explosion. A Cambrian explosion in the size and power of AI models. Every new dot you see on a chart like this represents a monumental leap in capability, all driven by this simple philosophy: bigger is better.
I mean, the scale today is honestly hard to even wrap your head around. Vision models have tens or hundreds of millions of those tunable knobs, the parameters. But the largest language models, they have hundreds of billions of them.
and they're trained for months on end using thousands of GPUs, crunching through datasets that represent a huge slice of the entire internet.
But this creates a huge problem, what the source material calls a compute schism. If making a top-tier AI costs millions of dollars and needs a warehouse full of computers, how can anyone else, a student, a startup, a researcher, ever use it or build on top of it?
Well, the answer lies in some pretty clever techniques. Instead of cooking from scratch every single time, we can use something called fine-tuning. This is like taking a master chef's perfect billion-dollar recipe and just tweaking the spices a little bit for your own tastes. You get to start with all of that incredible pre-existing knowledge and just adapt it, which takes way less data and way less computer power.
Another really clever trick is called quantization. This is a bit like compressing the recipe book. You're shrinking the model down by storing all those parameter settings in a less precise but still super effective way. This is what allows a massive model that was trained on a supercomputer to eventually run on something much smaller, maybe even your laptop or your phone. And these much more accessible models can still do absolutely incredible things. What you're watching here is a diffusion model, creating an image. It literally starts with random static, pure noise, and then, step by step, it refines that noise into a coherent, brand new image. It's like a sculptor seeing a statue in a block of marble, pulling a coherent idea out of pure chaos. So, it seems like we've pretty much mastered the recipe for creating these unbelievably powerful artificial minds in these giant labs. But the new frontier, the challenge that everyone is tackling right now, is figuring out how to move on from just creating them. How do we make them small enough, efficient enough, and useful enough to serve at everyone's table?